All right, welcome back. We are Game 3001. That's Game AI in the winter 2020 semester at George Brown, and we're week 9, part 1 of our broadcast. We're going to talk about template version 6 with memory optimizations using smart pointers. Let's talk about that a little bit. So I've updated your template, and I've given you a new one, template version 6. If you look up on Blackboard, please download that one already if you haven't had a chance to. I'm just going to copy it inside of here. Template version 6. That's taking its sweet time. And I'm going to rename this, so it's going to be called 8D. We're going to put it up on GitHub. So here's 8D, and just like before we start, like always, I kind of come into my command prompt, and then CD space. Here, I want to say git remote remove origin, and then when I set up, oh, wait. Git status. Git remote. Oh, doesn't have a remote. Good. Okay. Wonderful. That's nice. I don't mind about all this, but let's fix it. Let's add a remote. So I'll go up and GitHub. Not that one. We'll add a new repository. Less than 8. Yeah. Less than 9. All right, we'll grab these last 2 lines of code, and we'll go back to this and paste it and push it. Okay. Now let's do a git status. You can see that there's stuff I added. I'll say git add dot updated git commit -m. I'll say updated templates to v6 git push. So a couple commits, and you can see now when I refresh up on GitHub, I got 12 commits for this one. I have to tell you that I have modified many files on this one, like crazy amounts of optimizations, and I did that by following ReSharper's suggestions actually more than anything else. I'm going to go into 8D and double click to start off. So I want to talk about this template and what it is. So, as you know, in the past we had a bunch of memory leaks, right, in the template, and what I wanted to do was fix the memory leaks. So, if I run this now, let me take a look at the pathfinding example that I got going on. If I run this now, eventually when it runs, and it's just rebuilding, you're going to see that I'm not going to get memory leaks at all anymore. And let me show you this. So if I press 1, it takes me to my scene. I have some mines. I'll talk about the mines in a second. And notice in the process memory, I have about 45 megabytes, whatever that number is. Don't worry about the number. But if I was to move my planet around and recalculate my my numbers, you're going to see that I get a bit of a bump. Right? It goes to about 55, so slightly more, because what I'm doing is I'm converting the labels that are text into textures And there might be new ones that I've created. That's all this is doing. So this is going to create a bit more memory for me, okay? But if I keep doing this now, you can see that it doesn't matter how long I do this now, you can see that we're good, right? It's not going to increase much more. Also, if I go back to the start scene, you can see that it drops off. So it cleans up some of the memory, which we weren't seeing before. That's what we should be seeing. And if I go back again, you can see it jumps back up again. And if I just rejig it, you can see it's going to go back to something like around 55. And that's where the most is. Even if I change my ship around, or if I change, my mines, I redo my mines a bunch of times everywhere, I'm not getting a memory spike anymore like I was before. Well, if I increase the number of mines, so let's say I increase the number of mines up, I can do that. So you can see that I do increase slightly, a bit of a bump, which should, and I can increase all the way up to like every mine if I really want to, which is silly. And I can also go down to like one mine, right? So like there's a single mine somewhere. And I can just, there it is, there's my single mine, yay. Right, but that's not really the great test. I can go back up to like something like 50. I did this for you so that way you can test different scenarios out. It's really a test bed for your pathfinding. Does it work? And the way it works now is if I press F, you can see that there's a path that I follow that goes through to find the ship, to the planet. And what I can also do is I can use different heuristics. I have a heuristic change. I can go to, I want to find Euclidean distance. Well, maybe it's going to go this way this time with Euclidean, right? As opposed to the other way with Manhattan. Manhattan will go one way, and Euclidean will probably go another way, depending on the algorithm. Okay? So kind of different ways of doing stuff. I've also added some visibility options, so you can turn off the mines, right? I can turn off the planet and the ship, and I can just look at the grid. And I can even just take this away, so I can see the entire grid and the numbers on the grid. Okay, I can do that. So I've kind of added some additional functionality for you guys so that it makes it easier. So how did I do this memory management stuff in the first place? Well, there are some optimizations I found. So if I look at my config.h, online I found a really cool resource. And it basically talked about using a template function, right? And what it does, I'm not sure, have you guys done templating? Yes? You should have done it recently. So what this does is it returns something called a shared pointer, right? So here's my shared pointer. How you doing? So the shared pointer, it's different than what we've been using so far. We've been using raw pointers up until this point. Raw pointers, as you know, are managed by you. You create a raw pointer with a new keyword, and then every time we make a raw pointer, we got to make sure it's deleted properly and it gets managed, right? And if you don't delete it, what ends up happening is you get this memory leak potentially, right? That's what happens. So with a shared pointer, it keeps track of all the references that it has. It uses like automatic reference counting, kind of. And it keeps track of all the instances of that pointer. And then when we leave scope, what happens is it calls some kind of deleter function. This is the deleter function that it calls. So depending on the type of pointer that I create, a window, a render, or a texture, a surface, a font, the way this is set up is it chooses the deleter function that it's going to use based on the type of the type of pointer that the function is returning. So when I use make resource, and this is just, again, something I found that was really interesting online. For example, let's say I do a create window function. Well, the create window function, SDL create window, returns a reference to a window. And so the way to destroy the window would be used to this function, SDL destroy window. And so when it runs out of scope, it'll take care of it for you. That's what happens. Okay? So that is the way I did it. Where it gets funky is this stuff. It returns a shared pointer of the type that I want, but it passes in a with a reference to the deleter. This is the custom deleter with the type. Notice this part right here. This is kind of a lambda expression. That's what that is. And the lambda expression helps us return the right type, the right overload based on the type that I give it, right? So because the template, it looks at the type, and then it passes that type in to get the custom the correct custom deleter to clean up your code. Okay? High level. So that's necessary. And what I've done with the texture manager now, and again, the book recommended a texture manager, but one of the challenges that I had was SDL is written in C, and we're using C++, and some of the stuff that working together with C and C++ sometimes is funky. And so we had some weird disconnects with the texture manager. So here's an example of a texture map now. Instead of using a raw pointer, it uses a shared pointer. 3 types of very common smart pointers. One of them is a shared pointer. Another one is a unique pointer. Another one is a weak pointer. There's 3. Those are the 3 common ones. Okay. Unique pointer is interesting in that it can only have one instance ever. It doesn't allow you to count more than one time. You have to move the reference of that unique pointer to whatever's looking at it. So you can only ever look at that pointer once. A weak pointer is interesting in that you create automatic reference counting for it, but it allows you to pass something similar to a unique pointer around, right? Shared pointer obviously makes sense. It allows you, it's kind of what we're used to, and most of what we see in C# and Java and stuff is like it's using a shared pointer. It's always like how I feel about it. Or even in Swift, with automatic reference counting, it uses kind of like these, shared pointers for references. Kind of. I have to qualify it with that. Okay, so that's what it does. So we have a shared pointer now for each of the textures that are stored in the unordered map, right? And what we do is in the load function, one of the other memory leaks that we had, if I go to the load function, is when we load the actual object, the texture, right? We store an ID, right? That texture ID. And the texture ID could be like planet, mine, ship, whatever, tile, right? But every time I want to instantiate an object of type tile or whatever, I have to load the texture a bunch of times. But I don't want to load the texture more than once. I want to reload it, right? So what I had before is before I had this part here, and what this part does, it's a little utility function a friend of mine kind of wrote for me. We were talking about it, and he's like, why don't you just search through the unordered map and make sure that it's been cached? And I was like, why? Why would I do that? And he goes, because, man, whenever you load something in here, if you load the ID and you load it again, whatever this thing is pointing to, it's going to be overwritten. And I'm like, okay, great. And he goes, yeah, but you can't do that. And I'm like, why? Because whatever that pointer is pointing to is lost. It's going to be somewhere in heap memory afterwards. So this is one of the causes of my memory leaks right here. Okay. The other one, of course, was whenever we ran out of scope, there would be a problem as well. So that's the first change we made. And then, of course, I'm using this make resource thing, which I just talked about. Make resource, right? I said, okay, hey, texture manager, I want to make a temporary surface. I want to load up this file, right? Image load returns an SDL surface. That's what it does, okay? And it stores it inside this temp surface, and it's a pointer, right? So I wanted to make it a shared pointer now, okay? And as long as temp surface is not null pointer, well, we're good to go. We're okay. And then we pass in temp surface to create my texture from the surface. And notice that I need to use the .get method of the shared pointer. So again, if I was to look this up, let's look it up online. So if I say, C++ shared pointer, right? And if you look up the reference or the C++ reference for shared pointer, it talks about the shared pointer itself and what it is, right? And it also has a bunch of methods, and one of them is this .get method. Get method says returns a stored pointer, and that's what it does, right? You can still dereference it like normal. Everything is okay. I can also return how many uses that I have, right? And a bunch of other really cool things. So really cool, really good stuff. You can also make shared. It can create the shared pointer for you, and we don't need to do this right now because we're not making any one of those pointers shared. We're using the make resource function that does it for us. Okay, so that's this, and it also shows usage, which is kind of interesting. So you can see that here I have a standard shared pointer right? As an example, with a custom deleter, this shows you the deleter, and let me just take a look here. Here's your example code right here. So I have a base struct as an example, and I have a derived struct. And then what I want to do is I want to make a shared pointer from the base, right, as an example. And here we're using multi-threading. That's why we're using mutex and locking, right? And what's happening is, what this is doing is it's using a shared pointer to share. And one of the things that we want to do is we want to use pointers that are thread safe. And that's one thing that allows us to make pointers that are thread safe, which are smart pointers. So usually they're thread safe, which is pretty cool. And at least the way this has been done. Okay, so it gives you some ideas. So take a look at these resources online. There's some really great examples of this. There's not just these ones, but I believe you can also reference other types of smart pointers. For example, if I want to look at not just this one, but let's take a look at unique pointer. So C++ unique pointer. And you can see that it's different. It has similar functions. There's also a get for the unique pointer. But unique pointers are slightly different than shared pointers, right? So it says it owns and manages another object through a pointer and disposes of that object when the unique pointer goes out of scope. So it automatically does that. It disposes. There is no, and you can't do it. You can't keep the unique pointer. When it's out of scope, it's gone, right? So this is great to put inside of another object or some kind of for loop. And you can see this says the object disposed using the associated deleter, right? Well, we have to kind of set up the deleter for it to work. And if it doesn't know how to delete it, it will fail, right? So it gives you examples of how to do that down here with unique pointers, right? So again, a little bit out of scope from what we're doing. You should be learning about unique pointers in your algorithms class coming forward, okay? Actually, smart pointers in general. Okay, so that's what I did. So that's what this is all about. The texture manager uses smart pointers, and it helps us with our memory management, okay? So recommendations for you guys. If you're unsure of how to use this stuff or whatever, you can see that every one of my functions, my draw functions and everything else, uses the smart pointer. Please, I recommend, if you're going to use template version 6 for assignment 2, don't monkey with the texture manager or the font manager too much, because I've used them as functions for yourself. They're good, all the classes and whatever, but I wouldn't change it too much, because I've incorporated smart pointers and might mess you up. Okay? So that's smart pointers. Any questions around what I've done so far? More or less, what we have to think about is this is just our next iteration. Next week when we get together, we're not going to use pathfinding anymore. Our pathfinding's over after this week. We're going to be using decision trees, behavior trees, and state machines, right? So we'll be using this same template, but with a whole other thing that we're going to be creating, okay? Okay, let's keep going. So, yeah. But notice also we had our mines. I want to talk about the mines. So I created a object pool of mines, and I did that inside of my playscene.h. So starting off with playscene.h, I have a mine, okay? And the mine is just another pathfinding game object. And just like I did with the tiles, I created a vector of mines. I also have a mine number that I keep in the config file. The default number of mines is 50. I have 50 mines that come up online. I have a build mines function. Let's go there and take a look at that function. So build mines. And all I'm doing is I'm looping through 50 times, let's say, and I attach a mine to a pointer, right, as an example, and I put it on the display list. Here, what I'm also doing is I'm pushing back the mine on the mines vector, which is going to be used for our object pool. Okay? Now, curious, do I need to take care of the mine pointer here? Do I have to set it to null pointer, or do I care? What do you think? Do I have to do this? Do I have to do mine is equal to null pointer? Is that necessary? What do you think? I mean, I make a mine every single loop. Every loop, I make a new object of type mine pointer, right? Because if you notice auto, the auto keyword is like, it is implicit typing, right? So it doesn't say it is of type mine, right? It's of class mine, but mine itself is a pointer, a mine pointer type. That's what it is. That's what this is, a mine pointer type. So mine pointer, and auto basically figures out what this type should be by what I assign to it. So the assignment statement says, well, I'm allocating a new mine pointer object from the heap, and I'm returning a mine pointer. Well, then this must be of type mine pointer. That's how it works, right? It's still strongly typed, because once I assign that pointer, that type, it stays that way forever. It's not like a random keyword. It just automatically finds out what the type is. And auto is really great for long type names, like really complex type names or a template or something. Auto makes sense, okay? In fact, it'll even ask you to do auto here. Take a look. It says use auto for my loops, right? Because it doesn't make any sense to not use it. I mean, you can see that this is clearly an integer. And for future iterations, you don't know what this loop is going to look like. So curious again. So I made a mine, I added it up, and now I'm going to go back and make another one. What happens to the last one? Is it gone? Does it get automatically run out of scope? Or do I have to manage it myself? Probably should manage it myself, right? Because my mine pointer, even though it'll run out of scope, right, is still going to have like this, I might have a dangling pointer, right? So the reality is, though, that in this loop, once I ran out of scope, then it'll be cleaned up. Anyway, it's going to be cleaned up. But there's nothing wrong by doing it this way. And why? Because my mine, the actual the memory address of the mine that I'm pointing to is being held inside the mines array anyway. So I'm not really losing my memory, right? I'm keeping it. I'm not losing references. There's not really a memory leak here, except for the dangling pointer that I'm taking care of by doing this, theoretically. All right, so that's that one. I also erase mines, and notice that I can go through and delete the mine. This is using raw pointers again. I can delete the mine, and then I can set the mine pointer to null pointer every frame. I'm doing that, deleting it, sending it to null pointer. And then what I'm doing is when I delete all my mines, I want to set the mines vector to 0. That's what I'm doing with these 3 lines of code. Do I have to do all these lines of code? I mean, this would probably take care of it, but this is like making sure, and I kind of made an analogy that, it's like shooting a zombie in the head. You shoot a zombie in the head, and then you shoot it a couple more times to make sure it's dead, right? Which is kind of what I've done here, right? So that's what this does. Okay, and so I do a couple of things. I build my mines, I erase mines. When I reset my mines, I do this. When I'm resetting my mines, I also have to reset the impassable tiles. And right now I have a couple of, the enumeration looks like this. I can mark a tile as open, close, my start, goal, is it unvisited or impassable, or if the tile is a dead end, no path, right? That's what I can do right now for each of the tiles. So if you notice, if I go back to my code and run it, then if I press 1, you can see that if I press F, it's going to mark open tiles, right? You can also use find shortest path. It's going to mark open tiles until I get to my goal, from the start to the goal tile, right? By the way, again, if I change my heuristic, I might or might not have a different path, or not even find a path. So here you can see that it did this really weird roundabout down this way, right? Because of the tile values have changed, okay? That's all that's happening here. So again, if I go back to Manhattan, right? You can see that the Manhattan distance right now is from here to here. And one thing I've done for you guys is I've created this output for you on the console so you can track each one of the tile movements. And let me show you that again one more time. So let's play it one more time so you can see that. Here you go. So take a look. So now it's been activated. If I want to find the shortest path from the ship to the planet, if I press F, you can see that it calculates all these tiles. And if I backtrack for troubleshooting purposes, let's backtrack all the way to here. You can see that I got 17.7, 17.8, 15.7, and 15.6 in the tile values. That's what these are right here, right? So you can see that this mirrors what I see here, okay? And then, okay, cool. So where am I going to go now? Well, it's going to go down to 15.6. That's the lowest value. It clearly shows you that here. 15.6 is this way, okay? This one right here. All right, so now 15.6 is the middle tile. Where is it going to go? It's going to go to 14.6. 14.6 is the middle tile. Where's the middle tile? What's the lowest tile again? 13.6, right? And so on until it gets to where it's supposed to go. Now, there's going to be a point where it might have a similar value. Here's 8.3 and here's 8.2, 7.3 and 7.2. If I was going to go this way, you can see that I would have the same value and it would choose one over the other. Here, there are no same values. It's going to skip down here to this particular point, right? And it's clear the path it's going to take, okay? However, what if I move my planet around? So now it's way over there. Can I even find a path over there from here? Because remember, it's going to find paths based on the values, and sometimes it'll lead us into a dead end. The code I've given you guys is not the full code, obviously, right? I mean, this is your assignment, not mine, right? So you're going to have to find all the paths that are going to the goal, right? And you want to travel across the shortest path to the goal, right? The path I'm showing you is the first path that I found. This is not all the paths. Okay, so if I try and do this now, it might run forever or it might not. Look, it says the path length is 36. So I go here, it came down here, and it went across here. And you can see that it came across and over, right? And it went down this way, all the way down until it came all the way up. This is the way it worked. And this, again, is using Manhattan distance. If I try Euclidean distance, it's 26. It's shorter, right? It worked this way, came across this way, and then found its way down to this. Okay? Euclidean distance. Okay, make sense? So I'm just showing you this because, you know, again, you may or may not find a path. And I've done this, so when I respawn my mines, that's why I'm showing you this mine thing. Or if I increase the number, let's increase the number down to 100, all right? You can see for yourself, is there a path that takes me to the planet? Well, let's see. I can go down here, I can eyeball it, and there is a path that goes here, but it's going to be pretty convoluted, and there's a chance, there is a possibility that my ship might get stuck. Let's see if that's true. So if I say find shortest path, well, it found a path that's 30 length using Euclidean distance. So Euclidean distance found a path very similar to what it found before, went through here, went across here, and over here. What about Manhattan distance? Will it even find a path at all? And you might see something that goes like this forever. The reason why it goes forever, I'll tell you in a bit, but we should see it, no path. Okay? So again, I have no path, open, close, start, goal, and unvisited and impassable, and we'll talk about why it went forever in a second. Okay? Make sense? So when I'm resetting my mines, I want to look at all the impassable tiles and turn them back into unvisited, right? Because I want to reset, whenever I change anything, whenever I move my, in my little example, whenever I move my ship, whenever I move my planet, whenever I move my mines, I reset the thing again because I don't want to keep them the way they were, right? Okay, so when I spawn mines, I reset the impassable tiles every single time I do that, and I do a for loop. And when I run through a for loop, what I'm doing is I calculate everything based on the number of mines. Okay, so that's what it does. So let's say, for example, the mine number is 50. I spawn a new object. Spawn a new object we talked about last week, the week we were here. And what happens is it takes any object, resets the grid, if I need to, and then looks for a free spot on the grid. That's what this thing does. Keeps looking for an empty tile to put my stuff in. And then finally returns the tile index back out. So it returns the tile index back out. I can use it or not. And then I can look at that particular mine and get set the tile state to impassable. So whenever I spawn a new mine, I make the tile state behind it impassable. So again, if you run the code, and if I hide the mines, so let's say hide them, you can see that behind each of the mines is this impassable thing, right? An I for impassable. Okay, so that's what this does. And then I do something called a mine pass adjustment. This is more like a fine, kind of a path tuning that I've kind of put in place. So what does this do? It basically looks at every tile in the grid, and it says, okay, if three of its neighbors are mines, don't go with that tile. I got a mine. That's a dead end, right? I don't want to go there. Or if two of its neighbors and one, if it's on the edge and the edge is a null pointer, there's no tile there, right? If it's on the bottom edge or the right edge or the top edge or the left edge or combination of, and if those two things, the number of mines and the number of edges is greater than 2, then set that tile, whatever that is, to impassable as well. So that's an impassable pass. It passes through and marks stuff as impassable. So an example would be if you look at your mines, and you can see that in here, see this? There's like mine, and then in here, there's 3 mines, so it marks this as impassable. You can't go in here anymore. And same thing here, mine, and then there's a edge tile, which means this one is impassable too. So this is an area that the ship will not be able to go to. Same thing over here. However, it can still get stuck down here, right? And where is the ship? Well, the ship is way over here. Let's move it by pressing the M key, right? I move the ship. It's clear where the path is, right? And again, what I can do is I can just rejig the mine by pressing the E button. So I can do the mines again, move them around, until I can create a scenario where it's more difficult to find the path, like this one, okay? It may find the path, it may not. If I press find shortest path, you can see that it found a path that squirreled around. Look, it went down here, it came around, and then it went this way. Why didn't it go down this way? Remember I said that it's only going to take the first shortest path. So notice it goes down here, and then when it comes to this point, it says, okay, no problem. Well, this one is less than this one, so it's going to go this way. Okay? So that's what that does. So that's what this does. This basically, this mine pass adjustment, and I can have more than one. However, if I was to check for greater than 1, let's say I only had like 2 mines or a null or something like that. Well, if I did this, bad things happen. If I only said 1, let me show you what happens. If it's greater than 1, well, you're going to see that almost everything is impassable now, right? If you try this out, like watch. See? Almost everything. And if I try to respawn my ship, there's not too many places to go anymore. Like literally, because most of it's impassable, right? And same thing with my planet. I can move my planet around, but not too many places. Like there's only a few places they can go, right? Because the rest with the mine configuration are impassable. And same thing if I move my mines around. If I move my mines around, well, then it makes most of my area impassable with that setting, right? So don't put it that low. If you want to have another pass, we can do multiple passes. So notice it says first pass adjustment. Let's make another tuning. We can do some more tuning with it. Let's make a second pass, right, for the mines. I can do that. And if you tried that out, then what it's going to do is going to go through the first pass, mark some impassable tiles. And now because we have some impassable tiles already, it's going to mark it again. So example, these 2 tiles are now marked, right? Why? Well, let's take a look. So first it did its first pass, ran here and said, well, I got a tile here and a tile here and a tile here up here. And those 3 tiles are either null or impassable. Mark this as impassable. Cool. And then it does some other ones. And then it came back the second time around, right? And I said, wait, I have a mine here, I have a null pointer here, and I have an impassable of here. Mark this one too. That's the second time around it came through. So now this whole corner is the ship can't go here because it's a dead end, right? And notice it marked this one as impassable, which is pretty cool. And it may have marked other ones as well, like that one. That's a natural one. And I can do as many passes as I want, of course. I can do, let's do a few more. So we'll say, I don't know, we'll do 5 passes. And by the way, you could do this in a for loop, right? So we can say like for loop, do a for I, and we'll call this pass, right? And we'll say, I don't know, we'll do 5 passes. And we'll get rid of this one. And we'll say, adjustment. So this will do 5 passes. 5 passes. Just to, improve for tuning. So we don't have any like loose tiles. Now be careful. I mean, it's going through it and it's doing it 5 times, right? So you can see there's going to be areas that have more impassable tiles than others, potentially, right? So it goes through, it marks them, and you can see that this didn't really do much. It marked this one and this one, which is kind of what it would have done with the first pass. And same thing over here. Kind of marked this tile here, and this tile, because that's all it captured. A few tiles on the edges here. That's all it did. And it also captured some of these ones, but that was something that they were going to capture anyway, right? So if I do it again, if I just move the mines around, sometimes you can see that there's more passes. Okay? So I could totally do this if I want. And that's every time I spawn my mines, I do a mine pass adjustment. Let's do more. Let's do 50 passes. All right? See what happens with 50 passes. Right? I'm just being crazy, but let's try it, right? So, is it going to make a difference is the question. And to some degree, but it's only going to do minor adjustments, right? So you see even with 50 passes, only the ones that are like here. So this is where it was really nice. It was really effective here because it blocked this whole room up. This is like a block now, right? This kind of stuff. And if I move it around maybe a little bit more, you might see some cases like this whole area here has been blocked off. That's where that, and you don't need 50 passes for that. Okay, I'm saying this is what I did. And also when I increase the amount of mines, this is where it really becomes apparent, where it's really effective. So I can kind of move this to 100. It's about 100. And you can see that there's many more impassable tiles now, right? Like here where it's kind of basically shutting down some of these areas, but not this area. Right? Why? Because there's no tiles here. It doesn't matter if I pass through this 2 or 3 times. It doesn't meet the criteria. But here in this whole area here is blocked off. Right? This whole area is a big block, so it's not going to run in here. Right? Again, curious, is there a path to go to the planet? And yeah, there is. It's kind of convoluted, but it's there. It'll go down here, as an example, around here, and then it'll find its way around everything until it finds the planet. Right? So it's not so bad. So yeah, I could totally do that. I'm not going to. And you can see that there's not a lot of gain from it. Sometimes you want to add like, so single pass. Right. So that's kind of one thing I could totally do. Make this a little, this adjustment better. Other things I could do from an adjustment perspective is you could bias the tiles that are next to the mines. So anytime you have a tile next to the mine, you can increase the cost. Say passing by the tiles next to the mines they double the cost because maybe there's too close. And so you can make your ship avoid the mines, even going next to them, right? If you want, a little bit. However, be careful because they can still cause dead ends. Doesn't mean that that's going to solve the dead end thing. It just means that it's just the ship, you're just influencing where the ship is going to go. Okay? That's what's happening there. Okay, so pretty simple. And that's that part. let's keep going to the start scene now. So if I go to the start scene, you can see, or the start function, you can see that I set up my colors. This is the colors on my IM GUI for my buttons, my button colors. When I click on the buttons, they become that teal color, right? I build my grid, I build my map tiles, I make associations with all the neighbor tiles. I instantiate my planet and spawn it, instantiate my ship and spawn that, like we did before. Then I build my mines and I spawn my mines, okay? And when I want to, and if I look at my buttons here, in IM GUI, what I can do is I can change the heuristic. So this is the heuristic changes where I change my color, right? So that's how I pop and kind of change the color to whatever it's going to be, right? And when I want to rejig my mines, I do this. I say whenever I do a number of mines, I erase my mines first, I rebuild my mines, and then I respawn everything. That's what I'm doing there. Okay, so erase, rebuild, and spawn. And then same thing goes with visibility options. I can turn on or off visibility to ship, planet, or mines by using this little checkbox. That's what that does. And I can set this, I can toggle these values, these Boolean values, to true or false if I want to see them or not. And in the draw function, if it's not true, then I can't see my ship. It just won't draw my ship. That's what it does. So yeah, so that's what this does. And then in my input manager down here, when I want to use my, rejig my mines, I just spawn mines, right? So I don't delete them. It's the same number, so I just spawn those mines over and over again, and I do another pass. I clean up the ones that are already there, and then I do another pass of the mines, okay? So that's how I'm really doing it. One of the challenges I have, and I'm going to stop and take a short break in a second. One of the challenges I have is when I get stuck. And let me talk about this a little bit. So I can find something called find shortest path. Find shortest path, and how does it do this? It finds the lowest cost tile. Lowest cost tile, go to definition. Here's lowest cost tile. It has a heuristic for this, but really a lot of this is taken care of by the tile value. And the tile value you can find by going to the tile object. So if I go to game objects and I go to tile.cpp for a second, you can see in the tile.cpp file further down, I have this little heuristic which sets the target distance. And I have to talk about this a little bit. What I'm doing with it is it starts my heuristic at 0. And depending on which heuristic I'm using, it's going to set up the distance based on my heuristic. If I'm using Euclidean distance, then it's going to calculate h as the distance from the grid position to the goal location. That's what it does. If I'm using the Euclidean distance. If I'm using Manhattan distance, then h, the heuristic, is going to be the absolute value of the x, all the x's, and the absolute value of all the y's added together, and that's what h is going to be there. Okay, so that's what h is. However, I found that I got a lot of, I had to do some tie breaking, right? I ran into a lot of situations where the tiles were equal, especially on corners. So what I did was I created a couple of nudges. I created a Manhattan offset and a Euclidean offset. And what I did was I took the minimum from the Manhattan offset and the Euclidean offset and added them together, and then I got this offset, which is a small nudge, like really, really a small nudge. And you can see that they're really small, like 0.1, right? So if you take the Manhattan offset, all I'm doing is I'm taking the minimum of the Manhattan distance, whatever it is, on the x's, the minimum of the x's or the y's, and multiplying that number, whatever that is, by 0.1, okay? And then for the Euclidean offset, I'm taking the distance and I'm multiplying it by 0.1. And now I want the minimum amount. Whether it's the Manhattan offset or the Euclidean offset, I'm getting another minimum, and whatever that number is, I'm adding that on down here. So basically what's happening is I get the initial tile cost plus the heuristic plus this little offset, and the little offset, what it's going to do is it's going to just nudge me one way or the other, all right, slightly, like by 0.1. Okay, if not, if I don't do this, I'm going to get a lot of ties, okay? And I want a tiebreaker. Now, you may choose not to use this thing, and you may just choose to deal with each of these ties as a separate branch that you want to explore. It's up to you. Okay? This is what I did in my tile. This is how it works. So going back here then, what I do is when I want to find the shortest path, so if I go to find shortest path again, find shortest path does this. It says, okay, path length is 0. And then what I want to do, look to see is if my start tile, whatever that is not the goal tile, then let's find the lowest cost tile. Okay? And lowest cost tile, if I go there, what it does is it starts off at the top and it says, okay, I got my current tile, whatever that is. Let's set my minimum tile to null pointer and the min value to infinity. That's positive infinity, right? I'm also going to set up the tile number to 0. So the how many tiles, right? And as I loop through, I'm going to say this. I'm going to say, okay, cool. Let's set up an adjacent array, a vector of adjacent tiles. That's what this does. And I want to get all the neighbors, right? All the neighbors from my my tile, the current tile. And I want to just make a copy of them here in this adjacent list, or whatever. And then what I want to do is I'm going to take the current tile and display it. That's how you're going to see that display that I talked about before. That display tile is like a two-string equivalent, right? So it's like if I go here and I want to see, press F, you can see that this is displaying each of the tiles, the values of each of the neighbors. That's what this function does, display tile. Okay. And then what I'm doing is I'm looping through each of the neighbor tiles, each one, and I'm basically saying, look, if it's not a null pointer, right, and if it's not the goal tile, if it's a goal tile, then exit. But if it's not the goal tile, and if it's unvisited, so I don't care if it's open, and I don't care if it's closed, only if it's unvisited, then what we want to do is calculate if it's the minimum tile, minimum size, minimum value, if you will, right? So I can say, I start off with positive infinity and I say, okay, well, is positive infinity greater than, it's impossible to be greater than, right? Is positive infinity greater than this tile value? And if the answer is no, which it shouldn't be, right? If it's greater than, well, if it is, that's bad. If minimum is greater than, then if this is true, then minimum is now equal to this, whatever the value is, right? And then I can set the minimum tile to the adjacent tile and return if it's the goal tile. Okay. However, sometimes we get minimum as infinity because it fails this test. It comes through and it says there's no unvisited tiles. All the tiles are marked as closed or open or goal or start or whatever. And if that's the case, right, then I might get my minimum being infinity, and what that means is that there's no path. There's no path. That path I was following, there's no exit. It's dead end, right? So return that tile. Otherwise, if I pass through here, calculate the minimum value, whatever that is, and then start marking the tiles. And start marking the first tile, the one that's the minimum. Search for the minimum tile, mark that as open, right? Mark the rest as unvisited, the rest as closed, but only if they're already unvisited. If they're already open, leave them as open. If they're already closed, leave them as closed. And if there's something else, like impassable, leave them as impassable. But if they're unvisited, mark them as closed. Okay, that's what it does. And put that on the closed list. Okay? So that's what this little function does. But sometimes what happens is you won't find a path. So for example, I go to the path, and what I'm saying is if I don't find a path, right, then reset the grid and try again. And what's happening is this find shortest path is calling itself. It's a recursive function. We're going to talk about recursive functions in a second. Let's undo this for a second. Let's just not have it call itself. Let's just show a little message that says no path found. Okay? And let's try it now. So if I was to do that, undo. If I was to do that and start it now, there's going to be situations where there's no path found, and it's going to show an end. Right? Before it could go on forever. So here's an example. So is there a path from here to the ship? Looks like there is, but will it find the path from here to the ship? So if I press F, right, you can see that no, it didn't find a path. Why? not the first one. Take a look. It went here. It said, okay, it went, let's try and trace the path a little bit and figure out why in the first case it didn't find one. So we can see that the first tile here is 12.2 and the minimum tile looks to be 11.1. So it takes 11.1 into place. 11.1 has a mine next to it. Here's this is the one right here, 11.1. And the lowest cost is 10, which is down here. Cool, right? 10 seems to have a mine next to it. Well, it would because that's an impassable tile, right? So this is an impassable tile or a mine, right? And then I have two. I have 11.1 here and 11.1 there. 11.1 is already marked, so it can't go down that way. And there's also 11 by itself that's over here. Okay, 11, 11.1, 11. Which way to go? Well, I choose to go to the 11 because that's the shortest path. It goes back this way. Okay, didn't go back up this way. Can't go back up this way because the mark is old, right? And then, cool. From here, 11.1, you can see clearly on the map that's 12.0 is next. So I did what it's supposed to do, 12.0. And then from 12.0, it's going to go to 13. Right? So 12.0, 13 is the next one here. And it can go, now this is where we have branching. Okay? And this, my friends, is where you would do a recursive function. Say, okay, if we're equal here, go the other way, try the other side. We went, which way did we go? We went up. Right? We could have easily gone down. It would be the same result, but we went up instead, right? So we went up and we went across and we came to this point as an example, and then you can see that clearly 15.0 is less than 17.2. So it goes down here to the bottom, and then it finds itself here where there's only tiles we've been to before, and it stops, dead end. Doesn't know what to do from here. Why? Because all the tiles around it are either impassable, open, or closed. So what if I went the other way around instead? So I went up here, right? I came to this point, 13.0, and I came up to here, 15.1, as an example. Because again, you see that I went here, these are all the same values. So 10, 11, 12, 13. You can see I'm going backwards this way, right? And then I come up to 14, where I have 15.2 and 15.1, right? These are very similar costs, but I go here to 15.1. And I have 16.2 and 16.1, right? And I want to come down this way. But clearly, what I could have done when I was here, both 14.1 here and 14.1 here is the same cost. So what if I went down instead of up? So here I go down. Let's suppose I went down this time, right? This is closed, and so is this one. So I go over here, 14.1. 15.0, 15.1, 16.1, 15.0, 16.1, 15.1. Where would I go now? 14.0. I haven't gone up here before, right? Because remember, that's how, if I went the other way. 14.1, and I can't go down because I was here before, right? In fact, if I marked it, this one, I wouldn't even come here because this would be marked as C. So it would be here, 15.1, and it would go to 16.2. 16.2, you can see 17.3 or 15.2. I would go 15.2. 15.2 now, where would I go? Right? 16.3. 16.3, 15.3. And then, done. I'd be stuck. So whether I came down here or went up this way, using my path that I used, I'd be stuck. What about if I use a different heuristic? If I use Euclidean heuristic instead? Well, here you can see I'm also stuck, no path found, right? But I was stuck exactly where I said I was going to be stuck. See that? Using the other heuristic, because it went the other way, this way. So why am I getting stuck? I'm getting stuck because of the values. I'm getting stuck because of my decisions that I'm making, right? And what A star has to do is look at different paths until there's a short path to get to it, right? I'm only looking at the first path. That's not what you're supposed to do, guys. You're supposed to look at every path that has a length, right? And I haven't done that, okay? So please use the A-star algorithm, not the one I'm showing you here. Okay. If I rejig it, so if I change the mines, you can see now that there clearly is a path. But oh man, what happened? How come I went down into the ditch here? Well, look, even though there is clearly a path to here, right? Well, how did I do this? I went 10, 9, 8, 8, 7, 6, 5, 4. And look, you can see that 4.0 is less than 4.3. But because 4.0 is next to these two mines, and I've already marked these ones, this one is closed, just the way the position is. These two are closed, right? There's no place for this to go. And that's why it stops right here. Okay? So the decision point was, what about if I went this way? So for every time it goes, it should try and explore all the ways to go until it finds the shortest path. Then it takes that shortest path, or that path, and puts it on a path array, which we don't have right now. You don't have a path array for all the paths. And then what you want to do with that array is sort through those paths and find the shortest path that you're going to return back. Okay? You don't have that. You have no path right now. What about if I use Manhattan distance? Would Manhattan distance find a way? And yes, it would in this case. It goes up, it goes down, and then across, and it finds a path length of 13. Right? That's using Manhattan distance. Again, you're supposed to use one heuristic. I'm comparing both, so you can see the difference between one and the other one. Okay. So that's what this is. So I was using recursion before, but you could sometimes get into the point where you're getting into trouble. And the reason why we're getting into trouble here is because I really don't have a great base case. The only time I stop, if you notice, I kind of call my find shortest path again, and I go through this while loop, and it says, well, it's not the goal. Okay, but what happens if I'm back here to dead end again? Like, I got to break out somehow if I'm a dead end, right? But I want to try again and keep trying again, even if I'm in a dead end forever and ever and ever and ever. And that's not the solution, right? The solution is not me trying over and over again. The solution is trying different paths from different points. Okay? All right, so I want to stop this video right now, and I want to go into a different topic, and I want to talk about recursion a little bit, right? So I'm going to put this up on GitHub, stuff we've done already. So solution, I'm just going to, Team Explorer. I'm going to go to changes, and I'm going to say that removed recursion, which is what I did, from find shortest path. And now this is a state at this particular state in time where you would have to add in your own code to kind of hold all the possible paths using the heuristic. Okay. Again, for assignment 2, like I said to you guys before in lecture, you cannot use my assets. Use your own assets, please. Okay. If you want to do procedural or random content generation like I'm doing, it's okay, but you must guarantee a path. There must be a path for doing it. I'm not doing that with mine. I'm not guaranteeing anything. Okay? So if you want to make sure you want to use that, it's up to you. You don't have to. You don't have to make it random like I have to. You can make it fixed. You can make a fixed map with a few points that I can start. Point 1, point 2, point 3, whatever. And then I can kind of find if there's a shortest path using your tiling grid system. One more thing when it comes to assignment 2 is please make sure you give me a little document to tell me what to do. Like I mentioned that in lecture, but I'm reiterating that now because it might be cases where I don't get anything back. Okay, are we good? Can I move on? I'm just going to stop recording this one, and I'm going to come back and talk about recursion.